Hello, we're on to chapter 8. So now, since we've talked about alkenes and making them with the elimination reactions, now we're going to be talking about some of the additional reactions that we can do. So we talked about the doing hydrogenation, but there's a lot more that you can do. And the first real sets of reactions we're going to be discussing are adding groups across the double bond. So if you add, say, HX, so a halide, so HCl, HBr, whatnot, that H will go on one side, X will go on the other. You can add water across it, stuff like that. So now this is no different than adding this, right? Because you think of not H2O, but HOH. You had H on one side, OH on the other. Now you're going to have to put a little bit of an acid catalyst in there, and we'll show you how that works. You can also put in just regular bromines, things like bromines, chlorines, the actual the diatomic molecules here. But again, we're adding one on one side, one on the other, stuff like that. And so a lot of these mechanisms are going to work the exact same way, stuff like that. So the nucleophile here, stuff like that, because you're saying, well, that's a covalent bond. Why would that have negative charge? Well, we are putting 4 electrons between those 2 carbon atoms, and so there's a lot of electron density. So you're going to have a partial negative charge. You're going to take those 2 electrons from the pi bond, and actually you're going to get attracted to the hydrogen here, because this is a polar covalent bond. It's going to attract to that hydrogen. The hydrogen only needs one bond. So it's going to push those electrons onto the halide. Okay, so this double bond here is going to be making this new CH bond here. The problem is the other side of the double bond. The carbon only has 3 bonds now, so it's going to have a carbocation, which works out well because now you've kicked off the halide. This negative charge is going to be attracted to that positive charge. It's going to take one of those lone pairs, make a new attractive there, make this new bond here. So so this pi bond here, okay, is going to go to make this new CH bond. This bond here ultimately, initially it goes on to a set of lone pairs, but then it ultimately makes this C halide bond. But that's a lot of how all these work. Okay, with that, and so you're going to be adding across double bond, right? Order reactivity here. With that, and so you can actually get some selectivity, and we'll talk about that in a minute. If the molecule is unsymmetrical or non-symmetrical, stuff like that. So you can get H and Br on this side, or you can switch it to do H and Br on this side. Same thing goes with here. You can get it to go H and Br side, or you can flip it and put the H and Br on this side to make this compound. Now, how do we know that they're not going to make a whole lot of this? Well, there's rules. It's set up by Markovnikov, stuff like that. And so what it's saying is the hydrogen is going to go on the more substituted side of the CH bond. Okay, so you can also think of it as the H goes on the side with more CH bonds. Okay, and so this side has 2 CH bonds. This side only has 1 CH bond. So the H is going to go on this side. So that means the bromine is going to go on here. And the reason for this is the fact that it's all about stabilizing that carbocation. So if the hydrogen goes on this side here, on the left side of this double bond, you're going to be left with a primary carbocation. There's just not. It's going to be unstable. There's just not going to be a whole lot of this around for you to go and make the 1-bromopropane. Here, if you put the hydrogen on this side, on the right side here, this would allow it to be make a secondary carbocation, which is going to be a lot more stable. So there's just going to be a lot more of this around in order for the bromide to come in and attack to make the 2-bromopentane. So this is going to be that's going to be the main product. Okay, it's all about maximizing that carbocation stability. So in this reaction, right, you either have a choice. If you add the hydrogen on this side becomes a tertiary carbocation. That's going to be pretty nice. If you were to put the hydrogen here, you get a primary carbocation. That's just not going to happen. So if it did, what most likely would happen is you would actually probably get a hydride shift to move this over to make this carbocation intermediate, which would then just make more of that product. Now the question becomes, Well, okay. What if you need it to go the opposite way? What if you need the bromine to go on the less substituted side? Well, what we're going to do is we can't use the regular mechanism, right? So we have to change the mechanism. In this case, what we do is we add in. We can still add HBr, things like HBr, but we add in a little bit of peroxide, and that actually switches the order. And the reason for that, as it turns out, is that the bromide, because it's a radical reaction, the bromide is actually the one that adds first, and so it's actually going to add here because that's because what you want is the one electron system that remains to be on this tertiary carbon here. Then the hydrogen adds. So what you do is you switch the order of addition, and so the bromide goes on first, and the tertiary stabilizes what's left, and then the hydrogen adds. And so depending on whether or not you're in peroxide depends on if you get the regular Markovnikov or the anti-Markovnikov product. Okay, and so if we have, let's see what this one. So we have this product here. All right, so adding HCl. So we have two different ways we can do this. We can put on the Cl. Right? We can either put the H here and the Cl there, or we can put the Cl there and the H there. Okay, and so if you look at how the mechanism would go, you would have the carbocation here. If you added it like this, if you put the hydrogen on this side, the carbocation will go on the other side, and so this would be secondary. Okay. Here, the carbocation would be there, and so this one would have a 1, 2, 3 carbons associated. It's tertiary, so we know that for Markovnikov, because you don't have peroxide, it's going to you're going to put the halide on the more substituted side. So this is going to be the major product. Okay. So for this one, HBr, but in the presence of peroxides. Okay, and so for here, we need to know, okay, that's how many carbons are attached to this? Just one. It doesn't matter that it's a double bond. It's just you're looking at the total number of atoms, total number of carbon atoms here. So this is primary, right? This one has 1, 2 carbons attached to it, so that's secondary. So we know in the presence of peroxide, the Br is going to go on the lower numbered side, and so so the primary product is going to be having the Br there and that new H going on this side. Okay. Okay, so for the stereochemistry of this addition, okay, unless you, because you're going through this carbocation intermediate, that carbon is going to go flat. Remember we talked about this for the SN1 and E1 mechanisms. It goes flat, and so the nucleophile that comes in can either go through into the top face, which would make this compound, or it can come in from the bottom to make this compound. And so since there's no stereochemistry directing it one way or the other, you're going to get a 50-50 mixture of the R and the S, typically. Okay, so for the next one, we're going to talk about adding HOH across that, but it ends up following the same rules, but the mechanism is slightly different. Because we're in acidic conditions, okay, it's going to, the mechanism slightly change, but the products are still going to be the same. Okay, and so if we have this one, if we have this product here, okay, we're going to have HOH in the presence of a little bit of an acid catalyst. Okay, this is a catalyst. Now, a good rule of thumb is that when you're doing a mechanism, the molecule is probably going to react with that, almost always reacts with that catalyst first, and that's exactly what happens. So you've got this partial negative here from having all those carbons in there. So it's going to get attracted to here first because this has the positive charge, right? Not going to get attracted here because it's neutral, okay? And so you're going to end up with having the right. So you could either do one of two ways. You can either put that hydrogen there, put the carbocation there, or you could put the hydrogen there and the carbocation there. You do it either way, okay? So with that, and then the lone pairs on the water are going to react here or here. So with that, so if it reacts here, you're going to end up with you're still going to have those two hydrogens, right? The only thing you did is is use one of those lone pairs, so positive. Now, these electrons are going to get pulled in here, and what you essentially do is make the OH and then your acid catalyst back. Oop, you can't see that, plus H+. Okay. The other way you do it is if you would have the water OH there. And again, these electrons are going to go down onto the OH, and you're going to be able to regenerate your acid catalyst. It's H+. Okay, so now the question becomes, which is going to be the major? Well, this one, this carbocation here has 1, 2, 3 carbons on it. This one here, this carbocation here only has this one, and so this is primary, and so this is going to predominate the intermediate, and so this is going to be our that's going to be the major product. So rearrangements can occur with this hydration reaction. Okay, so with that, and the reason for that is the same reason why we had it before. It's all about stabilizing that carbocation. Okay, and so if you do that, so in this case here, so you have HOH, H+. Okay, so again, your double bond is going to react with your acid catalyst. Right, we're going to want to put the carbocation here and put that hydrogen there. Right now it's a secondary. If you were to move this CH3 group, move it over there, you would end up with a tertiary carbocation right there, right? So because there's 1, 2, 3 carbons attached to that carbon, that's going to be a lot more stable as a tertiary. Okay, and so then we can have that react and go on to make our product here. Just going to make the alcohol. Well, let's just go ahead and do it. You're going to make there. Oh, right. We're going to go ahead and lose an H+ to make this OH. Plus you're going to regenerate your catalyst. And so instead of adding directly on this double bond, you're actually adding the H here, that shifts, and then the OH is going on this side because of this hydride shift, or in this case methyl shift. Okay, so this is always a concern with using a hydration reaction like this. If you want to avoid this, okay, you're going to have to use a slightly different mechanism. And so with this one, what they found is that if you use this what's called oxymercuration, you can avoid those rearrangement issues. So it's still going to add HOH across there. It's still going to have the OH go on the more substituted side. Markovnikov says that's what's going to happen. But you do not have that issue of rearrangement. Okay, so you mix it with mercury. It's used traditionally mercury acetate. So the acetate is just like any other spectator ion. But you also have to include water in there. That's going to be your HOH. The OH part anyway. And then after that's done, you then dump in sodium borohydride, and that'll remove the mercury away. It's one of the few reactions in here where we actually use mercury. And so for the treatment for this one. So the reason why we want to use this is that, again, if we were going to use this molecule here, it's something similar. You get a rearrangement in here. You'd get a hydride shift. So here it's just a hydrogen that would shift over instead. But here you're only ever going to put that HOH across here. Now the OH is going to go on the higher ordered side, the higher numbered side. But you don't have to worry about the rearrangement issues. Okay, you don't even know the mechanism, but I'm going to present this to you. What ends up happening is the mercury actually associates itself with the alkene, with that pi bond. The water is going to attack and kick these electrons back up onto the mercury, and then the borohydride comes in, attacks at this site, and knocks off the mercury. stuff like that. But this, the mercury itself can stabilize the carbocation, and so that's why it's you don't have to worry about the rearrangement. Okay, and so by that, and so oh, well, here. So that's right. I forgot to change this, right? So I did. So I forgot to put this in, right? So if you have this reaction, you've got the oxymercuration, water, and then you hit it with borohydride. Next step, right? So for here, okay, this carbon, right, is primary, right, because it only has one other carbon attached to it. This one is secondary. The 1, 2, so with that, so you're going to want to put the OH on this side, and so you're going to end up with the OH on this side and that H on this side, or if you want to draw it, skeletal structure, it's like this. Okay, so what if you want to do the opposite reaction? What if your synthesis requires you to have the OH on this side? Well, there's a different reaction for that. There's a complementary reaction called hydroboration. This was developed by the H.C. Brown at Purdue, won a Nobel Prize for it. And so what he said is, okay, instead let's use borane or some derivative thereof, but this boron compounds and stuff like that. And so for there, when you the boron is actually going to go on the less substituted side, and it puts the hydrogen its hydrogen on the more substituted side, and then when you hit it with peroxide, the boron gets oxidized up, and so what you're left with on that carbon group is an OH. Okay, and so, but it is a syn addition. Do I talk about the mechanism? Yeah, I could say. So if you talk about the mechanism here, you've got the borane, the boron coming in here attacking. But it's all about a steric issue. The borane is a little bit bigger than that hydrogen, and so by that, and so just from purely steric issues, it's going to want to put that hydrogen on the less substituted side. It's just easier for it to get into. So that puts the boron on the less substituted side, just for sterics. So by that, but when they do it, it gets added on the same side, right? Because it's the boron's coming in and putting the stuff on the same side. Okay, and when that gets oxidized, it's a direct replacement of where that boron was. Okay, and so you get the syn addition. So they're either the H and the OH that gets added are either going to be on both on wedges or both on dashes. Stuff like that. So they're going to be adding to the same side. Okay, and so if we look at this reaction. Okay, we're adding water across here using the mercury acetate. Okay, sodium borohydride. Okay, and so for here we've got to look at right. So this side here has 1, 2, 3 carbons attached. So this is the tertiary side. That goes up there. This one here has 1, 2 carbons attached to it. So it's secondary. We know. With the oxymercuration, the OH goes on the higher ordered side, and so our product is going to go here. So the H goes on this side, the OH on that side. So if you want to look at this nice little summary, and so the acid catalyzed and oxymercuration, they're going to both give them our Markovnikov product. The stereochemistry is not controlled, so you're going to get syn and anti addition there. But the issue with the acid catalyzed hydration is that you do have issues with the rearrangement because you've got a standing, because you go through a carbocation intermediate. You don't have that with the oxymercuration, so you won't deal with that. If you want to get the anti-Markovnikov product, you use the hydroboration, and again, you're not going to get rearrangement with that one. Okay, you can also use this selectivity of hydroboration, stuff like that. So to actually, instead of putting an OH there, you can just put an H. So the net effect is actually the same as the hydrogenation. So you put the borane on there. So the BH2 is going to go on this side, and the H is so. So if you, the first step is the BH3, so you're going to actually get the H on this side and the BH2 on this side. But instead of adding peroxide, if you add acetic acid, CO2H, okay, what you end up doing is you end up kicking this off, and you end up with H and H across there. And like, well, why would you want to do that? Why don't you just do hydrogenation? Well, it's nice to have flexibility, because if you're looking at this molecule here, okay, it turns out that this portion of the molecule is actually sensitive to hydrogenation. So this is a benzyl group, and so if you did this reaction, you'd actually get a whole bunch of you would reduce this double bond, but this would turn into toluene. It would fall off. So with that, and so you would end up with this product and this product, when in fact what you really want to make is this. And so it can be a milder way of performing this reaction. Okay, so with that, so the only issue is borane is in fact explosive, and so you have to be careful about what kind of borane you use. So with that, you can also use this if you want to do put in the isotopes. So that, and so because if you do D2, so instead of H2 you do D2, the deuterium version of this, you would put deuteriums on the same side, but you would put it on both sides of the it'd be a syn addition on both sides of that alkene. Okay, and if that's what you want, great. But if you only want to put it on this side, okay, you could do this reaction, do the BD3, where you put where the borane would install the deuterium on the less substituted side. But if you hit it with regular acetic acid, the hydrogen would then go on to this side, and so now you only have one deuterium on there. So you can get, again, you can get a little more you get some flexibility depending on what your reaction needs, you know, for your product. So adding chlorine and bromine to the alkenes is it works very similarly to adding HX across the alkene. Now, fluorine and iodine, they have to go through slightly different ways. So HF is actually, F2 will actually react explosively with alkenes, so you have to be careful with that. Iodine's a little more sluggish. So you have to be, or it has to go through a slightly different way of generating things. So I don't know. So anyway, so with that, okay. So with that, but again, what you're doing, instead of adding like HCl across it, now we're doing ClCl. But the mechanism again is going to be exactly the same. But for this one, we have to take into account is the fact that you actually get it's actually anti-addition. So one is going to go up and one is going to go down. So the one chlorine on a wedge, one chlorine on a dash. Same thing with here. One chlorine on a wedge, one on a dash. One bromine on a wedge, one bromine on a dash. Okay, and the reason for that is what's called the bromonium ion. Okay, so this is probably the way it does it, but I always thought that it was hard to see what was going on. And so what's going to happen is, so if you have a double bond here, okay, you had BR, okay, so even though this is a polar covalent bond, okay, you do have these, remember the London dispersion forces, stuff like that, and so you can get a spontaneous dipole that establishes here, just because the electrons sort of wander over to this side, and so when you get that, the double bond can attack. Okay, so we only need one bond to the bromine, so it's got to do something with these electrons here, so it'll push them here. So push them onto the other bromine, just like the way HBr did. And so you can come in here, and that effect is it doesn't really matter which side you put it on. You're going to make that carbocation, okay, plus Br minus. Now, the thing is, you've got a positive charge here. You have a set of electrons here. They're going to be, the electrons are negatively charged, and so they're going to get attracted to this. And so you're going to actually get this resonance structure. And so with positive charge. Now, the bromine's not real happy because it's got a positive charge, but but this does form, and this is what's called the bromonium ion. There's also a chlorine version of it, so about that. But what happens is this blocks one phase, and so so in this case it's blocking the top phase. And so in order for this to for the bromide to come in and attack again, it's got to come in from the bottom, or in this case the opposite phase. Okay, it's got to come in from the opposite phase because the bromonium is blocking it, and so therefore you're going to end up with in this case you're going to have one BR up, one BR down. Okay. Now here it's symmetrical, and so you're going to get a mix of these two. But again, the bromines are going to be trans to each other. Okay. Now you do have to be careful, right? So with alkenes, you don't get it's going to lock it in. So again, you're going to get one up, one down, and so in some cases with the trans here, you're going to get a meso product here. If you rotate this bond around so the bromine's on the same side, you've got a nice mirror image here. But if you do the cis version, you're going to put one up, one down here, or you're going to put one up, one down. You actually make the two enantiomers. So be aware. So halohydrin is actually just an extension of this. And what's going to happen is instead of that last step, instead of the halide coming in and attacking, water is going to attack. So if you, so North Carolina, it's pretty hot and muggy in the summertime. So if you have, let's say BR, let's say you get a little bit of water in your solvent, okay? The reaction again is going to still be the same. So this is going to attack here, kick this away. So let's say that the bromine adds on this side and carbocation on the other. We can make this resonance structure here. Oh, sorry, Br minus. So we're going to make our bromonium ion. Help stabilize this. But instead of the bromide, because bromides can be a fairly terrible nucleophile, what's going to happen is now this is going to come in, or you can have it come in here. And so either way, and so what's going to end up happening is you get bromine on one side and you get the OH on the other. Well, okay, this has OH there. Release that back. Net effect is OH, like this. And so you get bromine on one side and the OH on the other. Okay. Now, and this is called a halohydrin. Okay. And so it actually follows Markovnikov's rules, because what you're going to want to do is again, you're going to have this carbocation formed that this can attack. So you can attack here. You're going to have the carbocation on a more stable carbon, and so the OH is, if it's going to attack somewhere, it's going to attack on the more substituted side. Okay. So again, the OH goes on the substitute side because you get a more stable carbocation intermediate. You're more likely to get it here because that if it's going to have the carbocation anywhere, it's going to be on that side because it's more substitute. Okay. So if we're going to do this is styrene, which is used for making polystyrene. So if you have ClCl, okay, so you dry DMSO. Okay. So what you're going to look at is to say, well, this one is nice because you're just going to add it across both sides, right? There's nothing else that can react, and so you have ClCl. Pretty easy. But if something happens, you grab an old, you do this next time your bottle of DMSO is a little bit wet, so wet DMSO, because DMSO can pick up water pretty fast. What's going to happen is now, since you have the wet, meaning that you have water in there, okay, so what's going to happen is you're going to add chlorine to the less substituted side and water to and OH on the other. Okay, so this one here, that's primary, right, because there's only one carbon attached. Secondary, and here, because there's two carbons attached, and so you end up with the OH here and a Cl there. You end up with a chlorohydrin. So, so for my test, I would specifically say water, but sometimes I've seen on tests where they say wet solvent, and that just means you have to recognize that that's H2O is present. So you're going to make the halohydrin instead of just a regular dye substitution. Okay, so cyclopropanes, stuff like that, and so these are coming into somewhat into vogue in drug design, and so what's happening, and so you can see these in a bunch of these compounds. So don't worry about the numbers. I just took this from this article, and so you can see this here for singular for asthma, a couple antiretrovirals here. So for anti-HIV drugs, there's a cyclopropane here and here. This one here is Suboxone for treating opioid addiction. This one is Onglyza. You can see the cyclopropane here, anti-diabetic, and this one here is to a platelet aggregation inhibitor. So it's to prevent blood clots. Here, Effiant, stuff like that. But they all have this, and this has been going on for the last 10 years or so. They've liked putting this in. So how do we make these, right? It's going to be difficult because there's so much strain involved with those cyclopropanes, stuff like that. And so what we have to use is what's called a carbene, stuff like that. So it's a carbon. It has two things attached to it, only two things, and a set of lone pairs. And so it is its formal charge is actually 0, but it is very, very reactive. Okay? And so we can't actually sell this in a bottle and stuff like that. And so you have to create it what's called in situ. You have to create it within your reaction, because as soon as it's created, it'll react, stuff like that. And so it's because the carbon, right? It wants to have 4 bonds. It only has 2 and a lone pair. Okay, so its octet is highly it doesn't have the octet. It's electron deficient. And so one of the ways that you can do this is actually with what's called diazomethane. And so you can, so if you actually draw this out, it's kind of a crazy compound. And so this actually has this has a negative charge. This has a positive charge, nitrogen here. This right here is effectively nitrogen gas. Stuff like that. And so when you hit it with usually light or some other inhibitor, what's going to happen is these electrons are going to go onto there, and you're going to make your carbene, and you're going to plus nitrogen gas, and this makes up 78% of our atmosphere. It's incredibly stable, and so you can get this, and so this actually reacts explosively. So if you want to give a chemical engineer heartburn, you just tell her you've got to scale up a diazomethane reaction. I mean, it's to the point where if you have a ground glass joint, if a little bit is trapped on, trapped on that ground glass, you put a little the grease in there and it gets trapped. If you were to put your if you make the connection, okay, and then twist it, and you get a little bit of that grinding, that's enough to set it off, and you get explosive. Your brown bond can go boom, stuff like that. But it's really good at making a carbene, stuff like that. So, and the way this works is this crazy. So if you have, say, a double bond here, what's going to happen is I want to make 4 bonds. So this is going to adhere to the octet. It's got to get rid of these lone pairs, and so you get the simultaneous. I'll give you a bond, you give me a bond, and we're all happy. And so you end up with this CH2 here. Okay, I should say, put this in black. Okay, and so these 2 carbons are these 2 carbons. This CH2 is coming from the carbene. Okay, now there's other ways of doing it. Okay, so with that, and so. One of the more inexpensive ways of doing it is actually chloroform plus base. So with that, so you actually have to be careful. Chloroform is generally a good solvent, although it's toxic and has other environmental issues. But it's a good solvent. But the problem is you can't run these in base because you can form the carbenes. And so what ends up happening is the double bond here plus chloroform, the presence of base. This is, you're going to make the double bond or the cyclopropane here, but because there's all these chlorines, you're actually going to you're going to have chlorines across it, and so your molecule is going to look like this. So you're going to have chlorines instead of hydrogens across here. which can be good. So with that, if you want a good leaving group. So with that, so the way this works, and the mechanism is a little weird. And so the first thing happens, right? So you have the base, okay, and your chloroform. So bases do what bases like to do. They grab hydrogens, right? Grab a hydrogen. You're going to put those electrons onto the. It's like any other base reaction, right? This thing's only interested in the hydrogens. These electrons can go on to whatever that hydrogen was originally bonded to. And so your base H, and then plus, you've got this molecule here, okay, this carbanion, okay? Now, this is where it gets weird. What happens is this chlorine just leaves, just spontaneously leaves. It happens slowly, but every once in a while it will. And so what you end up is this dichlorocarbene here, okay, plus Cl minus. Okay, now here is your carbene that can go and react with whatever double bond you have. Okay, it's this weird, I always say, well, what happened to that third chlorine? Well, it just goes away. Go figure. To make your carbene. Okay, so obviously the problem with this is that you've got chlorines here, and so are there other ways of doing this? Yes. And so the other one is what's called the Simmons-Smith reaction. And so what it does is that when you mix CH2, I should also mention, you can do this also with bromoform, and that puts bromines here instead of chlorines, obviously. If you want to just put a CH2 here, you do what's called the Simmons-Smith reaction. And so you end up mixing it with zinc copper amalgam, and that generates in situ your carbene. It's kind of an odd reaction. It's beyond this course, but you end up making this carbene, and it reacts. But the nice thing is now you're just putting CH2, and so if you have this molecule here, right, you do your Simmons-Smith. You take out that double bond and you put a triangle there. And so this CH2 here, CH2, like that. Cyclopropane. Okay, so for this one here, right, so you've got, okay, you've got plus the bromoform. OH. So you're going to put that double bond across here, okay? Take out the double bond, take out that pi bond, and so you end up with this CBr, Br. Okay. Now, if you notice, what's actually going to happen with the stereochemistry is that these groups here are actually locked into place, and so here they're going to stay where they are. So this is going to be on one side because the triangle comes in and just clicks right in. There's no time for rotation, and so this is going to point one way, and this side is going to point the other. Right? So you're going to get this is a dash, this is a wedge. If this was the if you need the cis version here, both of these would be pointing on wedges. Okay. So for this one here, here is the Simmons-Smith. And so again, you're going to make the triangle, but here it's just CH2. So like that. Okay, so for putting, you can also put two hydroxys on the other side of a double bond. Okay, so with that, and so the dihydroxylation. So this one is kind of a neat little reaction. You use what's called, you use osmium tetroxide for this. And so you take a double bond and you actually add OHs on both sides, but they have to be on the same side. And so you can also use this with cold potassium permanganate. But again, it's going to be a syn addition because the osmium is going to deposit its OHs. It's going to come down, bang. Put them on the same side, and then you're going to release the osmium back. Okay, and so those OHs are going to be on the same side. The permanganate does the exact same thing. Because both of the OHs come from the osmium, they're going to be adding to the same side. Okay. The problem is osmium tetroxide it's expensive. It's also very toxic, stuff like that. And so you usually use a recycling compound. So you only have to use catalytic osmium tetroxide, and so you add NMO, which looks like this, and so that'll recycle the your osmium tetroxide. Works really well. So you can also get cleavage of the double bond. So this is sort of like our molecular chainsaw. Okay, and so you'll see how that ties into the dihydroxylation in a second. So what we can do is we can, if we have an alkene here. Right? What ends up happening is you end up slicing this in half and then just putting an O where that double bond was. That's all you do. Okay. So if you had a triple bond, okay, so this would end up being C double bond O, O, and C. Okay. If you had a triple bond, now you're going to need to get 3 O's on either side. And so the way that we do the 3 oxygen bonds is actually with carboxylic acids. OH. Right, 1, 2, 3. Here we only had 2, so 1, 2. Here we had 1, 2, 3. So there you go. So you can do this. The primary way to do this is with ozone. Okay, and so I'm going to try and draw this large. Okay, and so when you work this up, so you do ozone and then work it up with either dimethyl sulfide, which stinks. But that's what they put in natural gas to give it a scent. Or you can do it with zinc and under acidic conditions. Again, what you're going to do is you're going to end up cutting, slicing here and then putting OHs here. But notice that there is a hydrogen here. And so when you do the ozonolysis, it's going to look like this. And notice how those OHs are pointed towards each other. When you unfurl it, it'll look like this, but it won't oxidize up that the aldehyde. And here's the mechanism. It's actually kind of a sort of one of those, like, I don't know if they've figured out exactly how it works, but there's a you form this initial the ozonide here, and then you form this right here. Kind of rearranges itself to make this this ozonide, and then it cleaves. So releasing dimethyl sulfoxide. Okay, with the KMNO4, if you do that exact same reaction, the aldehydes can't survive. Okay, and so anytime you're still going to get cutting here, and so if you have any aldehydes, they are going to, right, so there'd be an aldehyde here, right, this would get further oxidized up to the acid. Okay, it's the same products, but aldehydes get further oxidized up to the carboxylic acid. Right? So the reason why we're talking about that dihydroxylation is the fact that if you have this, if you do the osmium, okay, tetroxide reaction, so you do OSO4 NMO, you're going to end up with OH, OH. And it turns out that sodium periodate will actually cleave right here and turn those single bonds into double bonds. Now the OHs do also leave, but it's essentially the same as a ozonolysis. Okay, so it gives you the same products. Okay, but the OHs have to be pointing generally in the same direction. Okay, and so for carbon-carbon, just regular carbon bonds here, you can actually get free rotation around. So it's eventually, as it rotates, it's going to get to where it needs to go. Now for here, you have to be careful with the when it's on a ring. If they're both equatorial, that's close enough. But if they're equatorial and axial, it's probably not going to work. If they are both axial, it's definitely not going to work. Okay, so they have to at least be close to each other. Now, if they're both axial, right, you can get a chair flip to put them equatorial. That's fine, but you have to be careful. The other thing is they have to be right next to each other. They can't. If there's a carbon in between them, not going to work. Okay, and so for here, right, if they are, here you can get equatorial and axial, so they're at least generally kind of pointed down, that'll work. That'll be close enough. But if they're both axial, in this case, you can't do a chair flip because it's bicyclic. It's just not going to work. They're pointed in the wrong direction. So you have to be careful about that. Okay, so if we've got this one, O3, and then you do the normal workup acid, right? You're going to get the cleavage here, right? There's an H here, right? So you're going to end up with OH here, and then nitrogen like that. Just get a nice cleavage, no problem. Now for this one, oop. Now if you did KMNO4, right, and notice this one is, I forgot to mention the fact that, point out that this is the same reaction that you would use to put the OHs across here. This is generally done hot, stuff like that. And so again, you still get this cleavage here, but you would get this set of intermediates, right, because there's a hydrogen here, plus ketone, plus acetone here. This is going to be reactive, and so what you have to do is you have to, that's going to further oxidize to OH plus, in this case, this one. So you're going to end up with the two products, or the carboxylic acid here. Okay, so reactions with alkynes. Okay, and so with adding HX and just regular halides, so for that it's gonna work exactly like alkenes, except you just add it twice. Okay, but again, the CLs go, so in this case, if you're adding HCl, you're going to end up with an excess. Obviously, you need an excess of this, or at least two equivalents, right? The CLs are still going to go on the same side, Markovnikov, primarily. And actually, there's another reason, because when you form the carbocation again for that second reaction, you can actually get a resonance structure where the chlorine is going to help out. And so there's going to be a lot more of having the carbocation there in order for the second one to add. But it's just, you can just think of it as what Markovnikov told us we needed to do. Okay, now if you are going to add one equivalent of this, okay, you are going to get the trans addition here, right? So for that, so you're going to make that bromonium. It's going to probably block the one phase, and so the bromine is going to come in on this side. It's also an issue of sterics as well. Okay, so again, if you add HBr peroxide, say alkyne, you're going to get the anti-Markovnikov. Again, the alkynes in this sense work exactly the same as the alkenes. Okay, so you're going to get the anti-Markovnikov product. The issue comes when you have oxymercuration and hydroboration. The problem comes once you do that first one, you form what's called an enol, right? The ene for the alkene and the ol for the alcohol. This is actually unstable, and so what's going to happen is you get what's called a tautomerization, and you swap where the double bond is, and so this becomes a carbon-carbon single bond, and you make a carbon-oxygen double bond, and actually that hydrogen ends up down here. And so you actually form this. So as soon as you form this first one, it snaps into the ketone. No more alkene, no more reaction. Okay, so for that, and so if you do this for the oxymercuration, it also works with the hydroboration. If both sides are substituted equally, right? So in this case, secondary versus secondary, you're going to get a roughly equal mixture of the two. Okay, hydroboration as well. The issue comes with terminal. Okay, and so for this one, for this terminal one here, right? So you had secondary versus primary, right? So the OH is going to want to go on the secondary side. On hydroboration, again, we're going to go for this one. We're going to hydroboration adds to puts the OH on the less substituted side, the lower numbered side. So in this case, primary versus secondary, OH is going to go here. It's the same thing is going to happen with the alkyne. You're going to put that CO bond here. You're going to tautomerize, but now you got the aldehyde. Okay, so with that, and so if you run this. Right, we're going to do that's hydroboration. And the peroxide, right? So you're going to go through this, right? So you're looking at primary versus secondary. Okay? And so you're going to want to put that OH there. And so this is going to tautomerize to this. Right? There was already always a hydrogen here. And your hydrogen goes there. So this is going to be your product. Okay? Okay, so for the aldehydes, internal ones, and this actually works with alkenes with permanganate as well. Internal ones, you just get carboxylic acids on both sides, just like we talked. However, if you've got this, if it ends up being a terminal alkyne that you cleave, you end up, right, you've got an aldehyde here, right? That's going to further oxidize to carbonic acid, which then breaks apart into CO2 and water and stuff like that. And so if you have a terminal one, you're just going to basically clip off that that carbon and release it as water and CO2, and you're going to be left with just a carboxylic acid at the end. It's just your change is going to be one carbon shorter. Okay, so introduction to organic synthesis, and so we sort of talked about this in the last in the last chapter with the alkynes, but we're going to add a little twist to it. Okay, and so, but again, we're going to need to start with, so if we need to synthesize this OH, okay, we're going to need to say, okay, how are we going to put this together? Okay, and so usually what you're going to need to do is work backwards, and we're going to start with the functional group. So how do we put the an OH on here, and particularly one with on a primary carbon? Well, how do we know that? Well, so the way these slides are going to work. So this is the general reaction. This is how it's going to apply to this to our molecule here. Okay, and so this one here. So what we're going to have to do is we're going to have to, no matter what we start with, we're going to have to go through this intermediate here and then do the hydroboration. So BH3, H2O2. Okay, so how do we get to here? Okay, so how do we put that on there? Well, okay, well we can go through a some sort of triple bond. Okay, that's how we know how to make double bonds, right? You could also do an OH here, but hey, let's do a double bond here. So you need to do like H2 Lindlar. Okay, the lithium ammonia would also work, stuff like that. So again, but the reason why we want to go through here is that we know how to put, well, one, I think it said start with acetylene here and some sort of alkyl halide. So we need to get to a point where we have this CH3. So I forgot to point that out, that we needed to go through that acetylene intermediate. So here's our acetylene. And so we know how to put those groups on there, okay, by making this, going through this intermediate and then taking these carbons here, okay, and doing the SN2 reaction to kick this up, or to displace this. Okay, so we're going to go through here, and then we can get to this this intermediate. Well, how do we make? Well, so with this one we're going to just buy. So how do we do this? Well, we're going to take acetylene, right, and do the sodium amide. Okay, so you're working backwards. You start with your functional group. Okay, how do you get there? Now you can start thinking about, so okay, we need to go through here. Now we're going to start building up the carbon chain to get to this point. Okay, and if we needed to do acetylene here, so acetylene plus some bromide, okay, that's how we're going to proceed through. Okay. And so here's the retrosynthetic analysis, and so here to here to here to here to here. And so this is the actual reaction sequence. But we got to it by working backwards. Okay, and so if we needed to do this, okay, so we need to use any one of these components we need. Okay, and so bromide, right? So how do we know? How can we put the bromide? Right? Oh, it's on a primary carbon. So it's on the less substituted side. So the way that we know how to do that is HBr peroxide. Okay. So this, in order to do that, we need to have an alkene. Okay. Ooh, that's good. Right? Because we know how to make that because we can just, again, go through this well, let's do this time. Let's do sodium ammonia from our alkene. We know how to do an alkyne to an alkene by just doing that. We could also do the Lindlar, hydrogenation with Lindlar. Well, now we've got our acetylene, which we can here. Okay, and then all we need to do is get this 4-carbon piece here, and so we have to go through this. We need that acetylene anion here, and this 4-carbon bromide. Okay. And so how do we make this? Okay. So that would give us this product here, but now we're going to just start with that acetylene and the sodium amide. So we need this carbon, that compound, do the sodium amide, but notice how we figured out how to put on that functional group here to get to this intermediate. Now how do we get to this intermediate from one of these compounds? Well, then we have to figure out there. Once we can figure out, now we need to figure out how to get through this, how to assemble the carbon. So usually the first half is going to be just assemble, the carbon structure, and this is install the functional group. Okay, there's usually two parts to this, but you want to focus on this putting in the functional group first, because that's going to tell you how you need to assemble the carbon atoms in order to be able to do this part. Okay, so you're going to want to work backwards. So this is one of the ones I found. So it's cyclopamine. Cyclopamine. It's a potential antibiotic. It's produced by this penicillium compound. This component, I believe, if I remember right, it can lead to birth defects where you have where it looks like you're a cyclops. And so if cattle get into this and the cattle is born, it'll only have one eye in the middle of its forehead. But if you wanted to synthesize this, what you end up having to do is start building this part, right? So we needed to put this group in and go back, and you start working backwards, okay? And you start with D-proline, and you're like, what the heck? You would never start with D-proline and try to build it up this way, right? You have to go back to it. But if you can see, we needed this nitrogen ring here, this amine ring heterocycle here. So that's this part here, and so this is pretty cheap, stuff like that. And so and so we can start here, like that, move forward. Okay, good luck.